Okay, welcome to today's lesson. It is called the normal approximation of the binomial distribution. So, you're going to have to go through the first couple of examples to really get an understanding of what this title even means. So let's start with just a basic binomial distribution question. What is the probability of getting exactly 30 heads if a coin is tossed 50 times? Just to recap why this is a binomial distribution question, it's because we have discrete data. If our random variable is the number of heads, then you only have a certain number, a finite number of heads that you can toss. You do not have an infinite number of heads. You're not allowed to have decimals or anything like that. So we have discrete data. There are two outcomes. You have a success, which in this case is drawing a head, and a failure, which in this case is flipping a head, and a failure, which is flipping a tail. And our events are independent, which means the probability of success, which is flipping a head, is always 1/2. So that's why this is a binomial distribution question. So this was the formula for binomial distribution. And if you remember, n was the number of trials. So that means n is equal to 50. X was equal to the number of successes we were interested in measuring. So that was 30. And P was the probability of success. And a success in this case is getting a head. So that is equal to 1/2. And Q was the probability of failure. So if there's a half for success, there's a half for failure, because that's the probability of not getting ahead. Then using the formula, you have 50 C 30, and remember that gave you the number of branches, times the probability of success, and we want 30 successes, times the probability of a failure. So if there's 30 successes, that means there has to be 20 failures. And this all works out to 0.042. And that should be approximately equal to. So that's just your basic run-of-the-mill binomial distribution type of question. What we're going to be getting into today are examples that are a little bit crazier, such as this. What is the probability of getting at least 30 heads if a coin is tossed 50 times? Well, at least 30 means we'd have to find the probability of 30 successes plus the probability of 31 successes plus the probability of 32 successes, all the way up to 49 successes, and then all the way up to 50 successes. That is a lot of calculations. That means that you would have to use this formula 21 times. Nobody wants to do that. So there is one way that you could figure this out without taking too much time, and that way would be to use something like Excel. Now, using Excel, what we can do is we're going to put in the entire probability distribution. So we're going to start with 0 successes, and we're going to go all the way to 50 successes. And we're going to use the binomial formula for each of these. So to do NCR on Excel, you do COMBIN. And the n value is 50, and the x value is this. So we're going to start with 0 successes, and it's multiplied by the probability of success, which is 0.5, to the exponent of 0 successes, times 0.5 for the probability of failures, to the exponent of 50 minus the number of successes. So that's the binomial formula. So that's NCR. So if there were 0 successes, it would be 50C0, 0.5 to the exponent of 0, so no successes, and 0.5 to the exponent of 50, because if there are no successes, then there would be 50 failures. And then we can press enter. And using the power of Excel, we can just fill that formula down, and it will give you the calculations for every outcome. So it's going to give you the entire probability distribution. There's that answer for the exact 30 successes that we got for the first example, 0.042. So if we wanted to find the probability of getting at least 30 heads, what we can do is just take the sum of all the probabilities from 30 up to 50, and we found that that is decimal 1013. So we're going to keep that in mind for a little bit later on, but Excel is one way that we could answer that question. The problem is that we don't always have Excel handy, and back in the olden days, they didn't have Excel. So somebody who was investigating this found something interesting. What they did is they took the entire probability distribution and they made a graph. And what they got was this here, which, what does that look like to you? Hopefully you said that that looks like a normal distribution. If you were to have made a perfectly formatted histogram, this is what it would look like. And you can see it's got that bell shape to it. It is completely symmetrical on both sides. So this question can very closely be modeled by a normal distribution. So what we can do is use the process of answering a normal distribution question in which we find the z-score and use the normal probability table instead of using this formula 21 times. So this is what you're going to be learning, and this is what you're going to be tested on, is being able to use the normal method to approximate the answer to a binomial question. And that's the title, Normal Approximation of the Binomial Distribution. Using the normal distribution method will not give us the exact answer, but it will give us an answer that is close enough to save us from having to use this formula 21 times. Now there are a few problems with this. If you take a look at these three examples, the first one is the example that we've been looking at with the tossing a coin, and you can see that it is perfectly symmetrical and it is extremely normal looking. You could get some questions that aren't perfectly symmetrical, so you can see here that they're not exactly symmetrical, but they're really, really close to being normal. And that would be, this is the question, instead of flipping a coin, you're rolling a die 50 times. And then there's some binomial questions that don't look normal at all. This one is very much right skewed, and this is a probability distribution for winning the lottery. If you had 20 lottery tickets, and the probability of winning is 3%. So some questions that are binomial, you can use the normal method, and some questions that are binomial, you cannot use the normal method. And what it turns out is that if n times p is at least 5 and n times q is at least 5, that means the question is close enough to be able to use a normal approximation. So for instance here, n is equal to 50 and p is equal to a half and q is equal to a half. So n times p is 50 times a half, which is 25, so that's at least 5. N times Q is also 50 times a half, and that's equal to 25, so that also works. For the second question, N is 50, and if we're rolling a 6, the probability of success is 1 over 6, and the probability of failure is 5 over 6. So N times P is 50 times 1 over 6, which is 8.3. And N times Q is 50 times 5 over 6, which is equal to 41.7. So those are both also at least 5. Now, the further away these two numbers are, the more skewed this graph would be. So because these two are exactly the same, your graph is perfectly symmetrical. And for this example, N is equal to 20, and the probability of success is 0.03. So N times P is 20 times 0.03, and that is equal to 0.6. So that one is not close enough to being a normal distribution to be able to use the normal method. So if you wanted to answer this question, you would have to use the formula as many times as needed to answer the question. And sorry, time for another little editing interruption. These should be approximately equal to. These are exact and these are exact, but these are approximately equal to. So that's one problem you have to consider before you can start using the normal method to answer a binomial question. You have to check to make sure NP and NQ are both at least 5. If you are able to use the normal distribution method, in order to use this to calculate the z-score, you need to know the mean and the standard deviation. And these are the formulas that you would use for the mean and standard deviation. There's one more problem that you have to look at before we're ready to start. And this is where it gets a little bit complicated. Normal distributions only deal with continuous data, but binomial distributions deal with discrete data. So with continuous data, you can't really see a break in between 8 and 9 because this would be 8.5, 8.7, 8.9, 8.99, 8.99999. So there's no clear break between 8 and 9. Whereas with discrete data, you could have 8 tosses of heads or you could have 9 tosses of heads. You can't have 8.5 or 8.7. But if you were looking at height, you could have decimals in between 8 and 9. And this is one of the reasons why your normal method will only be an approximation of your binomial method. So what we're going to do is to take our binomial distribution and trick it into thinking that the data is continuous so that it looks more like a normal distribution. And this is what I mean by tricking it. If we were trying to find the probability of at least 10 in a normal distribution, that means that we would go from this point here and take everything to the right of that. So because we're starting here, we want to include the 10 bar because it's at least 10, so we want to include that entire 10 bar. If this was continuous data, right in between 9 and 10 would be 9.5. So instead of finding the probability of being at least 10, we would find the probability of being at least 9.5. And the reason we do that is because if you actually take that extra 0.5, you will get an answer that is closer to the exact answer than if you didn't. If you're looking at the probability of being less than 7, less than or equal to 7, we want to include the 7 bar because it's less than or equal to 7. And right here in between is 7.5. So if you wanted the probability of being less than or equal to 7, what you would do is actually find the probability of being less than or equal to 7.5. The last example here, x has to be greater than 12. That means greater than 12 but not including 12. So that means we would want all of this probability here. So it means we're starting after the 12 bar because it's not greater than or equal to. So this part right here is 12.5. So that would be the probability that x is greater than 12.5. So just to remind you, the reason we do that is because if we take that extra 0.5, we get a better approximation of the actual value than we would have if we didn't take the 0.5. So let's take a look at the example in its entirety. What is the probability of getting at least 30 heads if a coin is tossed 50 times? Remember that this is still a binomial distribution question, but because we have to go from 30 up to 50 and we don't want to use that binomial formula 21 times, there's too many cases to add up. That's why we're using the normal distribution method to get an approximate answer. Always remember you still have to start your questions with your start your solutions with your let statement. So let x equal the number of heads. Our n value is the number of trials, which is 50. Our x value, we want at least 30 heads, so at least 30. But we have to trick it. Instead of saying at least 30, that's going to be at least 29.5. If you're not sure, just draw yourself a little histogram and make this 30, 31, 32, 29, 28, because some people aren't sure, should I make that 29.5 or should I make that 30.5? So make yourself a little histogram. We want at least 30 heads, which means we want to include the 30. So that's why it's changed to 29.5. P is the probability of success, which is a half. Q is the probability of failure, which is a half. So we first have to check to see that we're allowed to use the normal approximation. So n times p is 50 times a half, which is 25. So that's at least 5. N times q would be 50 times a half as well. It's 25. That's also at least 5. So that means this data is normal enough that we can use the normal method. So now we need to find the mean and the standard deviation. So the mean, the formulas were on the previous page, is n times p. So that's equal to what we did above, 25. So this work is the same as this work. The standard deviation is the square root of n times p times q. So it's the square root of 50 times a half times a half. and that you're going to round to 2 decimal places. Means, if appropriate, you'll round to 1 decimal place. In standard deviation, you round to 2 decimal places. So this is equal to 3.53. And of course, that should be approximately equal to. So, from this point on, now we use the normal distribution method. So, we have to find the z-score. And just to remind you, the z-score formula is x minus x bar, which is the mean, over the standard deviation. So it's the data, which is 29.5, subtract the mean, which is 25, over the standard deviation, 3.53. Make sure you subtract the top before you divide. So that's going to be equal to 4.5 divided by 3.53, and that is equal to 1.27. So the probability of being greater than 30 is, because it's greater than, remember we need to take the number from the standard normal table and subtract it from 1. So using the standard deviation of 1.27, here is 1.2, and here is the 0.07. So it's going to be this number right here, 0.8980. So we're going to subtract 0.8980. And when you subtract that from 1, you get 0.1020. And again, a little editing break. Your z-score is rounded, so that should be approximately equal to. And your probability is rounded as well. So those should be, ignore that dot, those should be approximately equal to. So that dot should not be there. Approximately equal to. So because it is truly a binomial distribution and not a normal distribution, then this is just an approximation of the correct answer. And if you remember from our work with Excel, the correct answer was 0.1013. 1013. And that was our actual answer. So as you can see, they're not exactly the same, but they're very close. They're only about 1/1000th off. If you rounded it to 2 decimal places, they would be the exact same number. Again, if n times p and n times q were not both the same, if one of them was bigger than the other or much bigger than the other, then the approximation and the actual would be further apart than this. So that's why you have to check to make sure that you're allowed to use the normal distribution. So here's example 3. One bank has noticed that approximately 35% of loans in default are due to a sudden job loss. The insurance company projects that there will be 500 defaults in the next year. What is the probability that more than 200 of these loans are due to a sudden job loss? So in this case, our n value is 500. So that's your sample size. For x value, we want more than 200. Now again, you got to trick it, and you have to think to yourself, am I going to change this to 199.5, or are you going to change it to 200.5? So draw yourself a histogram to help yourself figure it out if you can't remember which way to either add or subtract the 0.5. So if this is 200 and this is 201 and this is 199, we want more than 200, which means we do not want to include the 200 bar. So we start from here and more than that, which means we're in between 200 and 201. So we're going to change that to 200.5. Now your probability of success, so if you let x be the number of defaults, the probability of success, so that's the probability of having a default, is 35%. And P and Q always have to add up to 1, so that means the probability of a failure is 0.65. We'll check to see if we're allowed to use the normal approximation. So n times p is 500 times 0.35, and that is equal to 175. N times q is 500 times 0.65. So that will be equal to 325. So these are both at least 5. They're not exactly the same. They do have a bit of a spread to them, so that means your answer will be a little more skewed, but they're at least 5, which means your answer will be close enough. The mean is the same as this because it's also n times p. So you really don't have to show this work again. You can just say that the mean is equal to 175. The standard deviation is the square root of n times p times q. And be careful when you calculate this. If you're going to start with the square root button, then you really need to have brackets around here, or else your calculator will only square root the 500 and not the 0.35 and 0.65. The other thing you can do is calculate what's underneath the square root sign first and press equals and then square root it after. Either way, you're going to get approximately 10.67 when rounded to 2 decimal places. So our z-score for 200.5 is the piece of data, which is 200.5, minus the mean, which is 175, and divided by the standard deviation, which is 10.67. And that is approximately equal to 2.39 when rounded to 2 decimal places. So the probability of being more than 200, again, this is more than. The probability in the table gives you less than, so the probability of more than is 1 minus the probability in the table using a z-score of 2.39. And for z-score of 2.39, so that's 2.3, 2.30, 31, 2, 3, 4, 5, 6, 7, 8. This is 2.39. And that's the number that we're going to use. So we're going to subtract that from 1. And that is approximately equal to 0.0084. So if you used Excel to add up all of these cases from 200 up to, 201 up to 500, your answer would not be exactly 0.0084. They would be approximately 0.0084, and that's why this is called the normal approximation. This is a binomial question because the data is discrete, the number of defaults is discrete. You can't have decimal defaults. There are two outcomes. You either default or you don't default. And it's independent because all defaults have a probability of 0.35. So this is a binomial question, but because we don't want to include all the cases from 201 up to 500, that's why we're using this normal method, which is a lot faster. Okay, so let's try another example. Calculate the probability that in 100 rolls of a fair die, a 6 appears between 10 and 20 times inclusive. Make sure you make your let statement. Here, X is the number of times you roll a 6. So N is the number of trials, which is 100 rolls. X is between 10 and 20. So we're going 10 to 20. So we're going to have to trick our data because it's inclusive. That means we include all of 10 and we include all of 20. So that means that changes to 9.5 and that changes to 20.5. Your probability of success is rolling a 6, which is 1 over 6. That means your probability of failure is 5 over 6. Oopsies, that should be a 6. So let's check to see that we're allowed to use the normal method. N times P, 100 times 1 over 6 is 16.7, so that's allowed. N times Q is 100 times 5 over 6, which is 83.3. So that's at least 5. So yes, we are allowed to continue. So the mean is exactly the same as this work. So the mean is 16.7. The standard deviation is the square root of N times P times Q, and that is equal to 3.73. Now, because we are finding the probability of being in between two values, hopefully you remember from the normal lesson that you have to find the z-score of each value. So we're first going to find the z-score of the 9.5, and we're going to find the z-score of the 20.5. So that would be 9.5 minus the mean divided by the standard deviation, and that is equal to negative 1.93. And the z-score for 20.5 is 20.5 minus the mean divided by the standard deviation, and that is equal to 1.02. Watch your rounding because it's 1.018, so make sure you round properly. So from the normal lesson, if you're trying to find the probability of being in between two numbers, you have to take the probability with this z-score and subtract the probability for this z-score. So we're looking for the probability of being between 10 and 20. So let's get the probability of 1.02. All right, here's 1.0 and here's the 0.02. So that is equal to 0.8461. So you're always taking the higher one and subtracting the lower one. And we're going to subtract the probability of this z-score. So for a z-score of negative 1.93, here's negative 1.9. So that's 1.90, 1.91, 1.92, 1.93. So it's 0.0268. And when you subtract those two values, you get 0.8193. Editing time. Alright, so we need approximately symbols here and here, and your standard deviation, your z-scores, and your probability. Don't forget those approximately equal to signs. So that's the entire method that you have to go through. It's a lot of steps. The steps aren't particularly difficult, but it's just remembering these steps. So what I'd like you to do is to press pause, try this last example, and then come back to the video to check your answer. So please press pause now and try this one on your own. Before I've explained this one to you, just remember that you have made your let statement. So let x be the number of purple candies, and there are 5 places where I put equal signs, and there should have been approximately equal to. So make that change, and then I will go over the explanation. Okay, welcome back to the video, and here we have our answer. So a lot of people forget to do this step here, so don't forget to do that tricking of the data. So we're taking that extra 0.5 both ways. Some other things to remind you of is if you have a z-score is off the chart, just use 0.9999 if it is off the chart on the positive end, or 0.0001 if it is off the chart on the negative side. Now you would be able to use technology to find a more exact answer, but since we're rounding to 4 decimal places anyway, it's going to be 0.9999. And because we're trying to find the probability of being between two numbers, you're going to subtract the probability of the higher z-score, subtract the probability of the lower z-score. And that should be your answer. So I know this was a long and maybe a confusing lesson, so hopefully you understood it. If there's anything you did not understand, please make note of it and ask your teacher in class the next day. Thanks and goodbye.